All right, welcome to the Calc 2 review. So there's a few of you coming in, so it's about 7 o'clock, so we're going to go ahead and get started. Again, if you guys have any questions or anything like that, feel free to unmute yourselves and ask a question or use the chat. So what I'm going to go through is, since we kind of covered the other sections of the previous recitations, I'm going to cover the later half of the material that's on the test. I advise you, if you haven't seen the other, if you weren't able to attend the other recitations and you haven't viewed them yet, they're on the website, they're through YouTube, so go ahead and watch those. I think it would be extremely helpful. I think you'll see something similar to some of the problems that we were doing on the test. So go ahead and check those out. So the first thing we're going to start talking about is approximating integrals. Now, from Calc 1, you guys should remember using left endpoint and right endpoint. So just kind of a quick review. If we've got some kind of parabola here, let me see if I can do my best in graphing this. Something like this for left endpoint. Let's go ahead and just draw the same thing for all of them. Basically same. Okay. So now for left endpoint, what we do is use these rectangles. We'll break this up now in these little tick marks here. What we do is we approximate this integral, or the area underneath this curve, by using rectangles and calculating and adding up all the area of these rectangles. So what we're going to do here for left endpoint is place the left corner of our rectangle on the function, right? And I'm going to connect the rectangles down once. Give it a second. Okay. Okay. So now I'm going to draw it down. So here we have these rectangles, and the area here, go ahead and use some highlighter, is the area of these rectangles here. And of course, you're going to have some error because it goes either under or over the curve. But notice that we're using only the left side of the rectangles on the edge of the function that we're evaluating. Now, you can imagine, of course, that the right endpoint is just using the right corner of these rectangles to do the approximation. Okay, so we're going to go ahead and approximate this guy. So again, now the area is approximated by these rectangles. Now, what midpoint does is, if we got these tick marks down here, instead of putting the rectangle on the function on the left or the right, what we do is we place it right there in the middle. So if we have this middle tick mark here, we're going to find where the function is there and then draw our rectangle. So we put some dots here right in the middle of each of these tick marks on the functions, and then do our rectangles here. Okay, so what we've got now is the area underneath these guys. And these are the three variations that you guys might remember from Calc 1. So now, writing these out in terms of our approximations, if you kind of remember, we've got the integral from a to b of f of x dx is approximately the sum of these rectangles. We're going to go from I equals 1 to however many we have, n evaluated at these xi star points, and then multiplied by delta x. Now delta x here is b minus a over n, right? Where n is the number of rectangles that we're using in that domain. Why I put a star on these xi's is dependent on which of these three that you're using, right? So if you're using left, make sure it's the evaluated point only on the left side of the function. But if we're doing right, make sure that it's on the right-hand side of that rectangle, right? Now, of course, the midpoint is going to be a little bit trickier, right? Because you've got to calculate in between these things. So that's where you're doing the function evaluation in between these endpoints for your intervals that you're using. So the first big one that you guys have learned now in this new section is trapezoidal rule. So we'll go ahead and write trapezoidal rule here. And you can kind of imagine what this is doing is we're evaluating our function here. Another parabola is for each of these tick marks now, I'm using both endpoints and then using a straight line to evaluate. And then making trapezoids out of them, and then adding up the area of those trapezoids. So I've written some stuff, but I don't see it on the, I think the screen is frozen. This happened before. Let's go ahead and see if we can fix this. Stop the share. This happened for the first recitation. I think it's just like the program that you use. It doesn't work that well. Okay, so we gotta go ahead. Okay, so you guys see what I've got in here? So I've got this trap rule here now that you guys can see, where we connected each of those endpoints to a straight line. So it's like a linear approximation. And we're adding up all the area of these trapezoids. Let me go ahead, just kind of highlight. Of course, the highlighter's not that detailed, so. All right, so how we write this out is we have our integral from a to b f of x dx is approximately, so again, we have our delta x here. We're going to divide it by 2 and multiply it by this expression. So we're going to have f of x naught. So that's the function evaluated at the first endpoint. And then something different happens here. We're going to have this coefficient of 2 on the function evaluated at the next mark. Then the function evaluated 2 times the function evaluated at the second, next 2. And then we're going to keep going until we get to the end. So this is going to be x minus 1. And then we're going to add, and notice that there again is not a 2 on the last one. So it's every evaluation point is 2 times within your region. So the endpoints, the x naught and the xn, are the only 2 that don't have this 2 factor. And that kind of comes from the fact that when you're adding up these trapezoids, they each have a height shared with its neighbor. And the end ones don't have a neighbor on that side, so you only get 1 factor. Okay. And with this, of course, there's always going to be error, and that's what we're going to kind of look at next is bounding this error. Where these kind of come from, it's going to take you a while if you want to keep going in math, especially in numerical analysis. But just take it, right? Just accept where these are coming from. So what I'm going to do is now write these guys out. So I'm going to bound the error on midpoint, so the subscript m here. And this is bounded by this factor k, which we'll talk about in a second. b minus a cubed over 24 and squared. And now the error for trapezoidal rule can be bounded pretty much almost the same expression. The only difference is this coefficient on the bottom is a 12 here. Right? So we have these two different equations here. So I'm going to highlight them so we can use them later. We got this pink guy. Let's do green. Yeah, green. All right, so we've got these two things here. So what is k? In terms of these two things, k is the bound for the second derivative. So the absolute value of the second derivative is less than or equal to some constant k. And where x now is in the region between a and b for this integral, right? So we've got our integration domain from a to b. The second derivative, the bound, how much the second derivative can possibly be, the magnitude, is bounded by this k. And that helps us find out what the error is. So remember, the second derivative is the concavity, right? So the concavity is playing a big role in what the error is. And if you can kind of see up on what we were doing before for the left, right, midpoint, and trapezoidal rule, the concavity really showed what was going to happen with the error, right? It's going to underestimate or it's going to overestimate. So that plays a big role in these guys. So that's why k is the bound of the second derivative. So now we can actually take the ideas of the trapezoidal rule a step further. Instead of doing this linear approximation, so the straight line from point to point, we can actually use a parabola, right? And this brings us to Simpson's method. So we got Simpson's rule here. So we're going to use parabolas. Now, what ends up happening, how you write this out, a to b, again, our f of x dx is approximately, again, we're going to have delta x. This time we're going to divide by 3. And then we're still going to have a pattern. It's going to be a little bit different. Again, the endpoints, the first one and the last one have a coefficient of 1. But now there's a different pattern. We have 4 times the function at x1, and then 2 times the function at x2, and then back to 4 times the function at x3. And then it alternates between 2 and 4. And then the second last one is going to be a 4 again. And then the last one, like we said, is going to have the coefficient of 1. Right? And now this is Simpson's rule. There's also a bound for this guy. So the absolute value of this error here is bounded by this k factor. And we'll talk about the differences of this k because it's not the same as up above. So the power that we've got here of the difference of b minus a is, it comes from the fact that Simpson's rule is actually more accurate because it's using a parabola rather than just a linear line. Now what this k is in terms of this expression is the bound on the fourth derivative. So very similar to the other expressions, just remember that it's the fourth derivative rather than the second derivative. Let's go ahead and highlight this guy. All right, so now we've got these expressions for our errors and how to approximate our integrals using left, right, midpoint, trapezoidal rule, and Simpson's rule. So these are all really good ways to approximate integrals. And we're going to kind of look at a problem that has applications. So let's say you want to approximate some integral with one of these methods, but you don't know how many intervals you should actually be using. Well, how good of an answer do you want? So let's say we've got, so the question is, what n do we need to approximate the integral from 1 to 2, 1 over x dx to within 0.0001 of our answer using the true answer using trapezoidal rule, right? So how many subintervals do we need using trapezoidal rule to get a really good approximation to within this 0.0001? So the very first thing we need to do is write out our function. So f of x in this case is our 1 over x, right? Well, the next thing we're going to need is those derivatives up to the degree that we want. In this case, if we go back to the other page, so we're using trapezoidal rule, which is the guy in green there. And so that k only needs the second derivative. So let's go ahead and find those. The first derivative of this guy is -1 over x squared. And then the second derivative here is 2 over x to the third, right? And now our interval is a to b, which is, in this case, 1 to 2. So if we kind of look at this function, 2 over x cubed, the bigger that x is getting, the smaller this whole thing is getting, right? So we're not going to be looking we're going to be looking for the smallest x value that we can have, as long as it's positive. If it's positive. So when x is 1, this is the largest that this thing is going to be. In this case, which is 2. So we can say that the bound on the second derivative, the magnitude of the second derivative is 2, and this is equal to k. Right? So now let's go ahead and write out, we've got our error here, and this is going to be equal to our 0.0001, which in this case we can just rewrite as 10 to the -4th. Right? Now this guy from our expression in green is this k b minus a cubed over 12n squared. Now if we plug in the stuff that we do know, we've got a 2 And then we've got 2 minus 1, so we got 1 there, 1 cubed over 12n squared. And this is 1 over 6n squared, right? So that means that we've got 10 to the negative fourth less than or equal to 1 over 6n squared. We can rearrange this guy, and then we've got n squared 1/6 times 10 to the fourth. And the only thing that satisfies this, so this is roughly n 40.8, right? Now on a test or something like that, you guys aren't allowed to use calculators. So these calculations will be a lot easier. Of course, you can kind of do this in your head as well, 1/6 of this 10 to the fourth. Just find out what 1/6 is in decimal form, and then move it 4 decimal places. And then you got to kind of take a square root, but don't worry. The questions will be rigged more so you can do them on your own rather than calculator use. So now we have got this n is greater than 40.8. Now n, remember, is how many intervals that we have. And we can't have 40.8 intervals. That doesn't make any sense. So our true answer here will have to be the next whole number, which is 41. Right? So if we have at least 41 intervals in our approximation using trapezoidal, we'll get to within this error. All right. So now lost the chat, so let me just double check. So some of you guys asked about Simpson's rule. Don't really worry about that too much. If Dr. Chang said you guys weren't going to cover it, then don't worry about it. It was just like a brief explanation of some better approximations that you can use. All right, so let's move on to improper integrals. All right, so someone actually asked a pretty good question here. So if n has to be greater than 40, right? So I should kind of carry through. So these guys right here just still be equal to's, greater than or equal to. So if you do have an integer, that's your answer, right? So if that was just 40, you would use 40 and not 41. The only reason that we're going up to 41 is because we can't have anything between 40 and 41 as a number of intervals that we're using. So yeah, that's a great question. If we have just 40 here, then the answer is 40. But if you have something in decimal form or fractional form, it's the next whole number that we need. Okay. So now let's talk about improper integrals. Okay, so let's say we've got something like 1 over x squared, right? And we want to know the area underneath this curve from 1 all the way to infinity, right? So this function is 1 over x squared. So writing this out, this looks like 1 to infinity of 1 over x squared dx. Now, this function goes on forever, right? And so what is the area underneath this curve? It's kind of strange to think about the fact that this area might actually be finite. It might be an actual number rather than infinity. If this function decreases fast enough to 0, adding up all these these really small rectangles will actually slowly get closer and closer to an actual number rather than just keep blowing out of proportion. We'll actually see this with this example. So a good way of thinking about this at first is, let's define a function, this area function, t, and it's equal to 1 to t of 1 over x squared dx, right? So now if we do this out, let's do this real quick. This is equal to 1 over minus 1 over t. So the area underneath this curve from 1 to t is 1 minus 1 over t. So if we let t get larger and larger and larger, let's say we actually take the limit here. So the limit as t approaches infinity of a of t, what is this equal to? Well, as t gets larger and larger, that second term, that 1 over t term, is going to 0, meaning that our area is going to 1. Right? So even though this thing is going off forever and never actually gets to 0, you are approaching this area of 1. And you guys will see things later on like this with when we're doing like infinite sums, when we're adding up an infinite number of numbers, or an infinite number, number of numbers. And you get to something finite. So if an integral like this just becomes something finite, that's called convergent. Now, the opposite could have happened. Adding up all of these really small rectangles could have given us something that was going to infinity, and that's called divergent, right? So convergent if it actually becomes a finite number, and if it's infinite, then we just have a divergent integral. Now, this isn't the only type of improper integral. So we're going to have another one, but before we go do that, let me just go ahead and write a clean way of writing these integrals, like how the book does it. So from a to infinity of f of x dx, the very first step you should be taking is writing the limit as b approaches infinity from, and then the integral a to b f of x dx, which is what we were doing above here for this example, right? We wrote another function that went from a to b, and then we just found the limit as this b, in this case t, went to infinity. Right? Okay. So the other type of improper integral that we might have is if we have a function that goes from a to b, and there's some point c in between a and b where f of c does not exist, right? So what happens here? How can this integral go through this point? Well, it might not, but it could. So how do we write that? You have this integral from a to b of f of x dx. Well, the first step we should be taking is going to the point, the problem point, the c, and adding up these two integrals. Now, we have it in a form that kind of resembles what we had above, where it's this problem thing. In this case, it's actually a finite point rather than infinity. What we're going to do is write out limits. We got c here instead. I'm going to write t going to c. Now notice that it's a one-sided limit because that's all we really need, right? Because it doesn't need to be approaching it from both directions for both integrals. It only depends on which side you're looking at for that corresponding integral. So in this case, it's c from the left. And then this should be the limit. T approaches c from the right. And t b dx. So what we've done here is we looked at this problem point in between A and B, broke it up, and then took limits from either side the way that the area that integral is actually calculating. So from A to C, we're looking at the left half. Maybe it's not half, but you know what I mean. This left half of this integral. So we only really need to know what happens at C from that particular side. Now, on the other side, that's why we have the plus. When we're looking at the right one, we need to know what's happening from the right. So that's a way to break up an integral that has a discontinuity somewhere in it. And let's go ahead and look at an example of doing improper integral. So number 2 here is 1 to infinity of the classic 1 over x dx. So the very first thing that we should be doing here is the limit as b approaches infinity, 1 to b of 1 over x dx. And we got to keep writing our limits out. Don't forget those. So we got the natural log from 1b now. And plugging in those bounds, natural log of 1 is 0. So we've got just our limit left over for the natural log of b. And this guy is going to infinity. So our original integral here is divergent. It doesn't approach a finite number. This is actually illustrated in the book. They do, they have this theorem here where the integral from 1 to infinity of 1 over x to the p dx, this guy is convergent if p is greater than 1, and divergent if p is less than or equal to 1. Why this is important is we're going to be doing a comparison test. And we'll talk about that in just a second here. Let's maybe go ahead and go to the next page for some, yeah, let's go to the next page for some extra room. So we have the comparison test. Right, and what is the comparison test? Well, sometimes we might not be able to integrate an improper integral using the techniques that we've learned in the previous sections. U substitution, trig substitution, partial fractions, integration by parts. We might not be able to use them. The integral might be too hard, but we can find out information about it if it's convergent or divergent. So let's say that we've got two functions here, f and g, right? Now, there's two cases for using the comparison test. To prove something's convergent and to prove something is divergent. And which way that you want to be going takes some practice and intuition. So I recommend going through your book, doing some practice problems. We're going to go through one in just a second, and you'll kind of get the idea. So let's say that we want to prove that G is convergent, right? Well, if we know a function that is always greater than it and it converges, then we know that G converges as well. Vice versa, if we want to prove that F is divergent, we need to show that something that's smaller than it is divergent. So then since F is bigger, it also needs to diverge. The distinction between which way these go is really important. A common mistake that I see in Calc 2 students is they will show that F is convergent because G is convergent. And that's not the proper direction, right? If you want to show that it's convergent, you need to show that something larger than it is convergent, right? So the area is smaller, and if you're smaller than a finite number, then you're going to be convergent. But if you're bigger than something that's infinite, then you're going to be divergent. So remember the particular order. It doesn't go both ways. So an example of this here is the integral from 2 to infinity cosine squared x squared dx over x squared dx, right? So we're left with showing that it's either convergent or divergent using the comparison test. So before you guys get started, why don't you guys just go ahead and send me, you can send me a private chat of your opinions on if you think this guy is convergent or you think this guy is divergent, because getting a good guess is the first thing we need to do, because we need to take different routes to prove either one. So go ahead and take a minute, check this guy out, and your initial guess if it's convergent or divergent. So I'm starting to get some opinions. Okay, so what we're going to do is actually check for being convergent first. That doesn't mean that this is the right answer or anything, but let's go ahead and check to see if it's convergent. To show that it's convergent, we need something that's larger than it. So let's start off by writing what we do know. The numerator here, cosine squared, can be bounded. Before I do that, let me go ahead and set this equal to I, so I don't have to like rewrite it a bunch. So we can bound this numerator here. So cosine squared is bounded between 0 and 1, right? Because cosine is bounded between -1 and 1, and if we square that, we're bounded between 0 and 1, always positive. Now, what we can do with this expression is divide all of them by x squared, right? And what this leaves us with is 0 is less than or equal to cosine squared x over x squared. And this is less than or equal to x1 over x squared. That's what we need. So we've got what we have inside the integral, our f of x, and we've got something that is always bigger than it or equal to it, right? And this is perfect. So all we need to do is show that this thing that's larger is convergent. So we're going to say that I here is less than or equal to the integral 2 to infinity 1 over x dx. If we can show that this integral is convergent, then I is also convergent. So what we have here is this integral is equal to the integral from 1 to infinity of 1 over x squared dx. And then we have to subtract that additional segment that we put in. Right, and the reason that I made it go to 1 instead of 2 is that I wanted it to resemble what we had here down at the bottom of the page. I wanted it to resemble this line here. Right, and if I can show, so P now is 2, right? And since P is greater than, or 2 is greater than 1, we know that that integral, the guy right here, we know that this is convergent. That's a finite number, right? So we know this is convergent, right? Now looking at this second integral here, what do we know about this guy? Well, it's properly defined from 1 to 2. There's no weird things happening. So we know that this guy is actually finite, right? It's not an improper integral. It doesn't have any weird things going on. It's just a normal integral, so it has to be a finite number, right? And if we've got something that's convergent, we know that that approaches a finite number. Actually, we know what that goes to. It goes to 1, right? So we have a finite number minus a finite number. So that means our I here is less than or equal to something that is finite. And we also know that it's bounded by 0, right? Because our integral from 2 to infinity of 0 is 0. So we know this is between 0 and a finite positive number. Let's go ahead and put a plus for positive, right? So we know that this guy's convergent because of that. And this is a proper usage of the comparison test. Now, let's go ahead and start talking about what we need to be doing for area between curves. So that's the last section that this test is going to be talking about. Let me go ahead. Area between curves. I think this is a pretty straightforward section. If it makes sense to you, awesome. I would concentrate on some of the other stuff, but don't neglect it. We're just going to talk about a little bit of the area between curves. So if we've got some kind of curve here and some other curve, so we'll go ahead and write green here as the area underneath this guy. And then pink here will be the area underneath the top guy. And you'll notice there's this segment that the green doesn't touch. And that's the area that we want, the pure pink segment. So how to write that is kind of straightforward. We have this area that we want. Let's go ahead and calculate all of the pink first. So if we go back here and define the top one as F and the bottom one as G, then we'll have the total area for this guy, right? So that's all of the pink. But that doesn't give me exactly what I want. I want just the pink, the area between F and G, not this gray section. So what I'll do is I'll just subtract the area of G, just the green stuff, right? And then notice that they have the same bounds, right? So we'll have f of x minus g of x dx. Right? And then this is what we use to calculate the area in between curves. Now, I think the trickiest part of this section is calculating the area between curves that don't look so nice. What I mean by that is, let's go ahead and look at an example of like just a rough sketch of something that might look a little weird to calculate the area in between. So if I've got my XY plane here, and then I've got this line, I'll actually do an example just like this shape. So I have my shape thing on. Okay, so the area in between these guys is a little weird. So this orange segment here, you'll notice that it's hard to break up where these things start and end in terms of like A and B, because the second one isn't even a function, right? It doesn't pass the vertical line test, right? If I drew a line somewhere down there, it passes through 2 points. So we could break this up and calculate the area in between where it kind of turns here and find the area there. Let's do a little better. There. Calculate the area in between there and then the lower half, and that's a lot of different integrals. What we could do instead is actually take our integral in terms of dy instead of dx. If you look at it as a function of y, it is a function in terms of y. So we can get away with just doing one integral. I think this is the kind of hardest part of this section. What I mean by that is instead of doing area going this way, like there's rectangles going up and down, we'll do rectangles going this way, right? So how do we do that? So let's look at an example. Let's calculate the area in between x equals 1/2 y squared minus 3 and y equals x minus 1, right? And the functions that I kind of drew over here are these functions. So this is what it looks like. So the very first thing we need to do is find which y they share when they connect. So the endpoints that I'm going to be using here are these green spots, right? I need to find those intersection points and what y they have. Those are going to be my a and b for my integral for dy. So I don't want their x coordinate, I just want their y coordinate. So what we're going to do is set them equal and find out when that happens. So we've got y plus 1. So that's the second equation manipulated, so it's just x, right? And then we'll set them equal. Is equal to this 1/2 y squared minus 3. And now we need just to solve this quadratic. So the next step for this guy, make it look like, just collect all the terms. We got y squared minus 2y minus 8. Factor this guy. This actually factors pretty nicely. It's y minus 4 and y plus 2. What this means is that y is equal to -2 and 4. So the y-coordinates of these green dots is -2 and 4. So that's all we need to start our integral here. So a is equal to the integral from -2 to 4 of our top one. Now, it's also a little bit tricky to find out which one's the top one. So remember that the lines are going left and right. So which direction is positive? This direction. So we have this positive side over here and this negative side over here. So the top one is actually the line. This guy right here. That's the top equation, right? So that's the linear term. So that's the y plus 1 term. We have y plus 1 here. And then we'll subtract our lower expression, which is this 1/2 y squared minus 3 dy, right? This guy is equal to -2, 4. We're going to go from -2 to 4. Just kind of collect terms here. Y squared plus y plus 4 dy. And this is equal to, now this is just a polynomial that we're taking the integral of. -1/6 y cubed plus 1/2 y squared plus 4 y from -2 to 4. And if you do that out, we get the area of 18. So we were able to change the direction that we were taking our integration to find the area in between these two curves, rather than using kind of a weird separation of these shapes to do the integral in terms of x. I think that's the hardest section. If you have two functions that you can easily take the integral in the x direction, then try to do the y direction. A little bit more complicated, takes a little bit more thought because you're not used to thinking up and down. So the reason that it's a y plus 1, I have a question. So the expression that we had for the line was this guy, right? So this is y equals x minus 1. So this x, so if we have a x equals y plus 1, that's our function in terms of y, right? So if we manipulate that blue equation to this is the equation in terms of y, and that's what we want. So solve for x in both of these equations, and that's your fy. Instead of vice versa, if you solve for x, that would be your f of x, right? So we want f of y, and that's what goes inside this integral. All right, so we've got about a few minutes until the end of the recitation. If you guys have any quick questions, I can't do any kind of like crazy examples from books or anything like that, but I definitely guide you in the right direction. If you're having trouble with any of these later topics, the internet is a great place to check out like some example problems. I know a lot of websites that present a problem to you and then give yourself some time, work through it, and then it will show you the details of how to accomplish the problem. So go ahead and hit me up with some last minute questions if you got any. If not, we're going to end the recording and give you guys some time to start studying for Wednesday. All right, so let me ask you guys this. What topic do you guys feel the weakest in right now? What seems like the most confusing? Is it the newer stuff? Is it the earlier stuff? Is it the integration techniques? Is it the approximation of the integrals? Is it doing improper integrals? Doing a comparison test? Or doing areas in between curves? Okay, so yeah, comparison test, I would definitely say is a little bit more difficult in terms of how you approach it. So if you want me to tell you that the further that you go in math, the more straightforward it is, then I'm sorry. So what ends up happening is you have to use more and more intuition on how to accomplish a problem or like solve a problem. And this is, I think, like one of the big first examples. So even though it's kind of binary, is it convergent, is it divergent? It's a little bit harder because you kind of have to have an initial guess and some background in solving these kinds of problems. So the reason that we went ahead and assumed that it was convergent is because, for number 3, is because we have this x squared term on the bottom. And we knew about convergence of, or divergence of integrals with 1 over x to the p. Well, p in this case was 2, and we knew that that was convergent. So all we needed to show was that this guy was going to be less than that. And the cosine squared is a really good example of something that's bounded between 0 and 1. And it kind of just gives way into, oh, screen kind of went away, but I guess it doesn't really matter. We can just still talk about it. So just go ahead and end the recording now.